today we're going to focus on a very unique and important type of stress state, which is a plane stress state, which is thin-walled pressure vessels. So hopefully you've heard about them before, but if not, obviously they're important in numerous applications. So oil and gas, you have pipelines, you have propane tanks, et cetera, et cetera. So thin-walled pressure vessels, and specifically cylindrical pressure vessels, are fairly ubiquitous. However, if you need some more information or more motivation, in 1919 there was the Great Molasses Flood in Boston, Massachusetts. So it was January 15th in the North End, where there's Mike's Pastries and lots of delicious Italian food if you've ever been to Boston. But on January 15th, basically molasses factory, the thin-walled pressure vessels burst. Molasses flowed down the streets of Boston in the North End at 35 miles an hour and killed 21 people, injured 150. And again, the reason, why did this happen? Well, if you've ever lived in Boston, the temperature went from below 0 to 40 F in a matter of hours. So obviously that caused those pressure vessels to kind of increase in pressure and burst. It is a critical kind of parameter, and we want to kind of understand this stress state. So very common scenario. Thin-walled pressure vessel with some, again, internal pressure, delta P, between pressure difference, delta P between the internal pressure and the environment. And the key thing, we could call something a thin-walled pressure vessel if we say that the thickness of our thin-walled pressure vessel here is, or this kind of here, this value here, if T is much less than R, our radius right there. So when do we know it's much less than R? Our R over T ratio must be greater than or equal to 10. If this condition is met, we can kind of basically apply kind of the derivation we're going to show in a second for a thin-walled pressure vessel. So if we meet this condition, what is the stress state of our thin-walled pressure vessel? Well, we're going to see in a second, it's going to be plane stress due to kind of not only due to symmetry considerations, but some assumptions that we're going to make. So we need to figure out what are the stresses in our system here, and we're going to do this by drawing some free body diagrams, so all the way back into statics. So first, let's consider the longitudinal direction, which is going to be our kind of one direction. So if we look at our thin-walled pressure vessel here, if I want to sum the forces in the one direction to make sure that they're equal to 0, when at equilibrium, free body diagrams, I need to make a cut that is going to be transverse. So I want to cut through my thin-walled pressure vessel like this. So if I do that, I cut here, there's going to be, again, some pressure being exerted on this, kind of this circumference right here, and then some restoring force back here. So again, there's some pressure right here. So there's going to be, so if I do sum of my forces in the one direction equal to 0, I'm going to have some pressure, some delta P, and it's going to be multiplied by, it's going to be exerted right here. I'm going to use this blue pen. So there's going to be some force right here. So that's going to be delta P times pi R squared. And there's going to be some, again, restoring stress exerted here. So that's going to be minus the sigma 1 times 2 pi, the radius, again, it's just through here, 2 pi R times T. So, and again, we're neglecting kind of the force here because we're just looking at the radius. Again, we're using a thin-walled kind of assumption. So when we do that, you sum those forces, you're going to find that your sigma 1, our longitudinal, is going to be equal to delta P R over 2T. So for this longitudinal section. So for the circumferential section, again, we need to take, if I want to figure out what's my sigma 2, or if I want to sum the forces in the 2 direction, again, the 2 directions going kind of along this circumference, the longitudinal direction is going lengthwise there. So if I want to sum the forces 2, making sure that those are equal to 0, again, I want to do the same kind of idea. I want to take a cut along this section right here. So I cut my cylinder, or my along that circumference in half, and I get this kind of, so again, I have some pressure that's acting on here, on this box. So I'm going to have, let's again calculate this out. So I'm going to have some, again, minus, again, depending on the sign. So in this direction, I'm having it going toward minus delta P times basically X So, or this delta x. The x, because again, it's just acting over this kind of, I'm going to approximate it as this kind of like square distance here. So delta x times 2r. Because again, I want forces. Remember, pressure, delta P is going to be pascals, which is going to be Newton per meter squared. So if I want forces, I need to multiply by an area. Same thing we did there. And here, the stress, the restoring, kind of stress coming out, that is going to be plus sigma 2 times what? There's delta x again, times the thickness, and then how many surfaces are there? So there's this surface and this surface, so I need to multiply that by 2. I get that right here, and then I will find that my sigma 2, or my hoop stress, can be equal to delta P R over T. And again, we're making kind of this assumption here that, actually not an assumption, we're only working on this area and this radius because, again, thin-walled, so our R, remember, is much greater than thickness here. So that's kind of the idea where why you're not considering, the whole, kind of picture there, and we're making kind of some assumptions in the geometry. But this is essentially our stresses for our thin-walled pressure vessel. So we have this hoop stress, longitudinal stress, and you'll see that the hoop stress is going to be twice as large as your longitudinal stress. So you'll expect the materials to fail along this hoop stress direction, i.e., so your material is getting you're basically stretching kind of the skin here. So if I'm pulling the material here and here, I should expect to see a fracture surface like this. If you see a fracture surface like this, that means there's some defect in your material, something is going wrong. And actually, depending on your material, you could find some kind of unique strain ratios for your hoop to longitudinal strain. So you'll see this will change depending on your materials, and you'll have a problem set question on that. Now, one question you may be asking, so this is what's happening. I have my thin-walled pressure vessel like this, thin-walled cylindrical pressure vessel like this. What's happening? Isn't there some internal pressure, like along, in the radial direction, like through the thickness? So let me draw this a little bit better. Try to. Isn't there some pressure going on here? Well, actually, there is some radial pressure along this direction. So you kind of look at this as inside, there's this radial stress that's equal to P. And outside, what's the stress here? Well, the radial stress outside is 0 because there's no internal pressure. So let's look at the magnitude of this stress here. So here, my radial stress is just P. What about my hoop stress? Well, I know that thickness, that R over T value, let's take it the limit where R divided by T is equal to 10. So I know that my sigma 1 is equal to 5 times this sigma R, and I know that my sigma 2 is equal to 10 times sigma RR. So because of this, again, and this is our limit, we're just allowed to kind of use this thin-walled pressure vessel value. We're going to assume that because of this, thin-walled pressure vessel, that we're going to be able to neglect this component, that through thickness, that radial kind of stress. And the reason is, again, thin-walled pressure vessels. You can see this is an order of magnitude larger. This is 5 times as large. Again, at the very limit, usually this is much larger than 10. So that's kind of the scenario that we're working with here. So instead, we can neglect this, and your stress state for a thin-walled pressure vessel is just going to look like this. So it's going to be your sigma longitudinal, again, depending on how you orient your, so if I draw my system like this, actually if I draw my system like this, where it's 1 and 2, it'd be my hoop stress, my longitudinal stress, everything else is 0. And then I'd have my hoop strain and longitudinal strain. And I could write that out. You all are experts at this now. From your E, sigma hoop, to sigma L. And the same thing here. Minus nu sigma hoop. That's it. So you could kind of now go and approach and solve any of these kind of problems with thin-walled pressure vessels. And there will be several of them, and you'll definitely have them on problem sets and on exams. So work on those and do well on those. All right, I'll see you on the next video. Thanks. Bye.